Hi, good afternoon, ma'am.
Good afternoon. Yeah. So, good afternoon, everyone. Uh, so, we are into the sixth lecture of social media analytics. Okay. So, before starting today's lecture, I would like to announce that the assignment has already been uploaded, and this is an individual assignment. You have to do it individually. And also, like, there are four data sets in that assignments. So, you can choose any one of the four data sets that you want. Okay. So, yeah, with that, we will start with our lecture today. Okay, so this is a quick recap of what we have done in our last lecture. So in our last lecture, we have seen the traversal algorithms, the depth first search algorithm, then the breadth first search algorithm. We have also seen the shortest path algorithm, that is a Dijkstra's algorithm. So we have done an example, and through the example, we have tried to understand that how Dijkstra algorithm works. Then we have seen minimum spanning tree algorithms, the Kruskal algorithm and the Prim's algorithm. We have also discussed that how both these algorithms are different. Then we moved on to some social media analytics measures. So first one that we discovered was the clustering coefficient. So first measure that we discussed was clustering coefficient. And after that, we moved on to a very important question in social media analytics. That is, how do you identify important nodes? Okay, so the important nodes are called as central nodes, and there are various algorithms that we have seen in our last lecture. So you can identify the importance of a node based on degree. Then we have studied closeness centrality, and we have also studied betweenness centrality. So these were three different notions, and like if we are calculating it by using closeness centrality or by using betweenness centrality, the meaning of the centrality changes from one algorithm to another. So the whole intuition in social media analytics changes. Okay, so when you are using these different algorithms. So, in today's lecture, we will be majorly discussing one very important centrality measure, that is eigencentrality measure. Okay, so this is another way or another intuition of finding how central a node is, and it is based on the importance of the neighbors and the importance of neighbors, and so on. Okay, so before we move on to the mathematical part of eigencentrality, okay, so first I would like to start this lecture with a small example. So this is a very interesting example. Okay, so for example, you visited a city, maybe Mumbai. Okay, so you are in a Mumbai, and then after work, you feel like going to some places. Okay, and you don't want to see the Wikipedia for important places because you feel that it's very personality oriented. Okay, so in this case, what you will do is, you know that there's one of the friend that is called as Ramesh. So there's one friend in Mumbai. You'll call that friend and you'll ask that what all are the places that I can visit in Mumbai. Now, this friend suggests you that, okay, you can go to beach. Okay, you go to beach, but then you found that place very, crowded, and you don't like even the food there. So you are dissatisfied with your visit there. Okay, so now next day again after work you are free, and now again you want to visit some place. So now, tell me, would you call Ramesh again? So maybe no, maybe I would think of another friend who is living in Mumbai, and then I'll call that friend. So let us suppose that friend is called as Raj. Okay, so Raj suggests me a bookstore. He says that this is a bookstore near your hotel. You can go there and you can read books there, and there's some cool stationery. So, yeah. So, based on his suggestion, I visit this bookstore. Okay, and I really like that bookstore. I really enjoyed there. So now, next day. So now, next day, like again, after work, I'm free. Now, next day, whom will I call? Will I call Ramesh or will I call Raj? So the answer is definitely, I really enjoyed what Raj suggested. So we will call Raj. Okay. So Raj then suggests me to go to a coffee place. So now I again go to the coffee place and I enjoyed the coffee place. Okay. So there is some scenario or some social media analytics that is going behind the scene. So the thing is, you visited this coffee place or you visited the bookstore. Okay. So you like this coffee shop. So you give it a good rating. Okay. So you like this coffee shop, you give it a good rating. And when you come back, you also give good rating to the person who suggested it. Okay. So similarly, when he suggested the next place, even the next place you liked, okay, again you come back and in your mind you give some rating to the person who have suggested this place. Okay. So this is called as progressive, this is called as incremental progress. Okay. So generally what happen is, if you have good recommendations, okay, if someone is recommending good things, so then the trust in that person increases. Okay, so this is the general scenario that we see in our day-to-day lives, and this is also the scenario on which various companies work today. Okay, so now I give you another analogy or another example of a repeated improvement in the network. Okay, so for example, I am working in a lab and I have a supervisor. Okay, so in my lab, my guide or my supervisor, he is guiding really good. Okay, so now because he's guiding really good, so I'm able to publish good papers. Okay, so because I publish good papers, so I am growing in my career. So because I am growing in my career, even my guide is growing in career. Because he is growing, even I am growing. So this is repeated increment in the network. So this phenomena, this particular phenomena of repeated improvement is usually seen in social networks. And today we will try to see that how we can quantify this repeated improvement in the networks. Okay, so now, till now, we have seen that, okay, there is some notion of repeated improvement in the networks that are around us. Okay, so let's try to quantify this and let's move back to the example that we were discussing earlier. So previously, we were discussing the example of two friends that were Raj and Ramesh, and they were suggesting some places. Okay, so what we can do is we can consider the places suggested by them as a list. Okay, so there is a list that is suggested by Raj, and there is another list that is suggested by Ramesh. Okay, and these are the places. These are the places that are suggested by Raj and Ramesh. So generally, this will happen that better rated lists lists will suggest better rated places, and better rated places will be suggested by better rated lists. Okay, so this is a vice versa relationship between better places and better list. So the rating of the places and the rating of the list grows hand in hand. Okay. So now let me take another example. Okay, so till now, what we have studied that, okay, we have networks, and in networks, generally, we have this scenario where like people are giving feedbacks about or suggesting certain places. So based on the feedbacks, we give rating to the places, and the rating to the places affect the rating of the person, and so on. Okay, so now you have seen that in the network there are these two type of nodes. So one is the person who is suggesting the place, and the other node is maybe a place that is being suggested by. Okay, so what is the difference between these two type of nodes? So let's try to understand with the help of an example. Okay, so let us suppose I have this class. of around 50-60 students. Okay, so in the class, I have asked students to solve a problem. Okay, so now all the students they have a problem to solve. Now, like in the class, they discussed among each other. They discuss among each other that whom should we go to solve this problem. Okay, so now there are many people who are pointing to this particular student, maybe Sonia. Okay, so many of the people they feel that okay, if we discuss this problem to Sonia, then maybe like we would be able to solve this problem. Okay, then even this node, the Sonia node, is again pointing to some other nodes. Okay, so now you can see that there are two type of edges in the node, in the network, that is incoming edges and the outgoing edges. So based on these, we can divide the nodes into hubs and authorities. So based on the directions of the edges, we will divide the nodes into hubs and authorities. So in the coming slides, we will be discussing what all are hubs and what are authorities. Okay, so now there is another intuition in this particular example. So suppose, okay, so generally in the networks, good nodes will point to good nodes. Okay, or in other words, I can say that important nodes will point to another important nodes. Okay, or in the other hand, I can say that important nodes will be pointed by another important nodes. Okay, so that this definition or this terminology will be more clear when I further discuss the examples. So, okay, so each node in the network can be quantified by two scores. Okay, so first one is, are good people pointing to you? So this is the first score. Are good people pointing to you? So that is one type of quantification. Okay, and there is another type of quantification, that is, are you pointing to good people? Okay, so take some time and try to understand the difference between these two. Okay, so the importance of a particular node depend on these two aspects. Okay, so there are two aspects in the networks that can be quantified. So the first one is, are you being pointed by good nodes or good people? Okay, and the other one is, are you pointing to another good people? If you are pointing to good people, then you become good. Okay, or in the other words, if you are being pointed by good people, then you become good. So these are the two notions, and they are captured by the notion of hubs and authorities. So now one by one, I will be explaining you what are hubs and what all are authorities. So when I'll discuss these definitions, this concept will be further more clear to you. Okay, let's read these points. A node can be given points, or a node can be quantified as hubs and authorities. Okay, a node is a good authority if it is pointed by good hubs, and a node is a good hub if it is pointed by good authorities. Okay, so don't worry about this confusion. So let's first discuss about hubs and authorities. Okay, so let's first clearly try to understand what is the difference between these two and how do we quantify first hubs and then authorities. So up till now, any doubt, anyone? Yes, the quiz will be scheduled tomorrow. Up till now, is it clear what I'm explaining? Okay, so now we will move on to the definition of hubs. Sorry. Okay. Okay, a hub is one of the example. So it will be more clear when I discuss one example from real life social media networks. So let us take an example of citation network. Okay, in citation network, you know that there are papers and then paper refer to other papers, and based on that, we form a network. Okay, so now we generally have survey papers, and survey papers contain a lot of references. Okay, so it contains a lot of reference to the state of art work. So suppose this is a survey paper in the citation network. So because this is a survey paper, so definitely it will have a lot of references to other papers. Okay, so other state of art papers. So the survey paper in citation network becomes the hub. Okay, so hub is a node that points to other nodes. So hub is a node that points to other popular nodes. In citation network, the paper that refers to important paper, like a good survey paper, is an example of a hub. Okay, now how do we calculate the hub score? So just now we have discussed that we can quantify the importance of a node based on like hub score and based on the authority score. So how do we calculate the hub score? Okay. The hub score will be summation of all the edges that are outgoing. Okay, so maybe this is maybe A1, A2, A3, A4, A5, A6. Okay, so the score of this hub will be A1 plus A2 plus A3 plus A4 up till A6. Okay, so this is how we quantify hub score. Now next, see, in hubs, what is important is like a node's outgoing edges are important. Okay. Now, what is the definition of authorities? In authorities, the incoming edge are important. Okay. So authority is that how authoritative you are in the network. Okay. So that will depend on how many people are referring to you. Okay. So how many people as well as like whether they are important people or not. So these two things will quantify that whether you are authority in that particular network or not. Okay, so let's again move on to the definition of citation network that we were seeing before. So now maybe there is this citation network of all the papers in maths, okay, or all the papers in graphs. So now there is one paper on Dijkstra algorithm. Okay, so definitely there will be a lot of work that will be referring this particular paper. And there will be a lot of paper with high citations. Okay, even the papers that are themselves referred by a lot of other nodes. So even though those important nodes will be referring this paper. So because this particular paper is being referred by so many other paper as well as by important paper. By important, I mean those hubs that have high citation. Okay, so those papers that have high citation, for example, this survey paper that we have seen in the previous example. Okay, so if I have this particular node, that is this particular paper, that is paper on Dijkstra algorithm. So this node is an authority node in the network. Okay, so for the authority node, it is important that we calculate the cost that is being added by its incoming edges. Okay, so now how we will calculate the cost of an authority? So cost of the authority will be cost given by all its neighbors. So it will be H1 plus H2, so on up till maybe I think 6. Okay, so yeah, so let's read this slide. So authorities, these are the nodes that are themselves important. That are themselves important and they are pointed by a lot of other nodes and by important nodes. The authority score is sum of all the hub scores of the nodes pointing to the authority node. Okay, so the authority score can be mathematically written by using this formula. So up till now, is the definition of hubs and authority clear to you? Any question anyone wants to ask? Okay. Okay, so till now we have seen the mathematical formulas of authorities and hubs. So whenever we have the network representation in the form of adjacency matrix, okay, so we have already seen in our previous lecture that how you represent your networks to the computers. So in that lecture, we have seen there are various different ways to represent the networks. So one of the way was to represent the network through adjacency matrix. Okay, so in the form of adjacency matrix, this is how these are the two formulas that shows us how the authority score and the hub score is calculated. Okay, so now these are two very important points of hubs and authorities. So it's important to discuss this point because like the definition of eigencentrality is built up upon all these concepts. So it's very important to understand this concept if you want to understand that how we calculate eigencentrality. Okay, so by discussing these definitions and by discussing these intuitions, we are slowly, step by step, moving towards the calculation of the eigencentrality. So yeah, these two are mutually dependent. So as I have already explained with the help of the example, so we have already seen the incremental progress in the networks through two examples. One was the guide and the student network we have seen, and the other was the places suggested by two of the friends. Okay, so we have seen how incremental progress works in the network. Okay, so now this particular slide says that the hubs and the authorities, they are mutually dependent. How they are mutually dependent? A good hub points to good authorities. Okay, and a good authority will be pointed by good hubs. The mathematically hubs and authorities scores always converges after repeated iterations. Okay, so now repetitively, see, when we started a lecture, so we have seen that the trust in Ramesh's list was increasing. Okay, and was increasing as I was following that particular list. Okay, so what it says is that mathematically these scores or these ratings will slowly converge in the network. Okay, so now we will see that what do we mean by converging? Okay, how these scores converge. Okay, so for now you can understand this key there is some maths going on behind in the network. Okay, so that is some kind of score. So we are calculating some kind of scores that is derived by like how much rating is given, or there can be other measures to give those ratings. So we are calculating those ratings iteratively. Okay, iteratively means repetitively we will be calculating, and slowly those values will converge. Okay, by converging means that they will become constant. So now how they will converge or how they will become constant. So we will work through this example again to understand the concept of convergence of the scores in the network. Okay, so now we have this network A, B, and C. Let me just draw this network on my iPad. Okay, so if you want, you can work out this example along with me. So I'll give you 1 minute to take out pen or paper if you want. You can work out this example along with me. Okay, so I'll start. Okay, so this is the network. Okay, so initially, let me assume that there are some resources that are being equally distributed in the network. Or in the other words, I can say that each and every node has equal power. Okay, so let us suppose the resource was one and I have divided it into the three nodes. Okay, so each node will get 1 by 3, 1 by 3, 1 by 3. Okay, so now here I will try to calculate the values of these resources iteratively. Okay, so suppose we have these three nodes A, B, and C. Okay, and initially I had a resource that was one and that is divided equally in the network. Okay, so now all the node has equal score. Okay, initially at first step all the nodes have equal score. Okay, so now let us try to understand what will happen in next iteration. Okay, so now we know that all the nodes who have outgoing edges, they will try to distribute this value to the other node. Okay, so now we can see that A is connected to one other node, that is C. C is connected to one other node, that is B. So there's one outgoing edge to from C to B. So C is distributing its score, or C is distributing its rating, or C is distributing its resource to B through one edge. Okay, so there is only one edge through which C can distribute. And if we look at B, there are two outgoing edges here. So B is distributing its resources to two different nodes. Okay. Okay. So now at next iteration, let us suppose, let me just erase these codes. Okay. So now in next iteration, A will distribute its resources to C. Okay. So C will receive 1 by 3. Now again, C will distribute its resources to B. That is 1 by 3. Now B, the node B is distributing its resource to two other nodes. So what it will do is it will equally divide that resource. So A will get 1 by 6 and C will also get 1 by 6. So is it clear to everyone, this calculation? So by the end of next iteration, A will have score 1 by 6. B will have score 1 by 3 and C will have 1 by 3 plus 1 by 6, it's 1 by 2. So up till now, any doubt? Anyone?
Get 1 by 6. I thought it would be 1 by 3 plus 1 by 6.
1
A.
by 3? No, there's just one incoming edge, right?
It had 1 by 3. Where did it go?
It has given its resource to C.
Oh, I see. Okay. All right.
Yes,
All right.
yes,
Yeah.
yes. Yeah. So this is the second iteration. Now let us see what happens at third iteration. Let me again erase these scores.
Ma'am, in this way, C has also given it to B, right? Then
Yes.
why we
So
are counting C?
C has given its score 1 by 3 to B. Okay, C has given its score. Just a second. C initially had 1 by 3, so it gave it to B. B had initially 1 by 3, so it has divided its resource to both A and C. So it will give 1 by 6, 1 by 6. Okay, and then A will give its resource to C, that is 1 by 3. Is the calculation clear to everyone, or should I repeat?
Can you please repeat from the start? Means what is the initial values each are having?
Okay, sure. Okay, so initially we have seen that A has the value 1 by 3, 1 by 3, 1 by 3. ओके, अभी के लिए आप ये अज्यूम कर सकते हो कि ए बी सी जितने नोड हैं उनको हम कोई भी इक्वल वैल्यू दे सकते हैं. Okay, so for now we have given them values 1 by 3, 1 by 3, 1 by 3. Okay, why we are giving this equal values? Because we mean to say that, okay, all these nodes, they have equal powers. Okay, so whenever like we are giving feedback or like we are giving suggestions, okay, so that time all are having equal power, so all will be initially having same values. Okay, so for now everyone is having 1 by 3, 1 by 3, 1 by 3. Okay, अब B जो है, B is distributing its resource to both A and C. तो what it will do, it will divide its resource. ठीक है, 1 by 3 को आप divide करोगे by 2, 1 by 3 divided by 2 will be 1 by 6. So it will distribute 1 by 6, 1 by 6 to A, 1 by 6 to C. Up till now, is it clear?
Yes, ma'am.
Hmm. अब A जो है, A से तो there's only one outgoing edge. Okay, so A will distributes its entire resource जो कि 1 by 3 था to C. So it will become 1 by 6 plus 1 by 3.
So
What
how we
C
are
will do?
deciding that when this distribution is happening? Because now A has 1 by 3 from itself and it
We are
also receives 1
considering
by
it,
6 from B. So
yeah.
ultimately A has 1 by 3 plus 1 by 6. Can A give all everything to C now?
No, no. So we are considering these scores based on what was the previous score, not what is being calculated now.
Okay.
Initially तो like first step में जो भी score है उसको base लेके you have to do the calculation. Is it clear? Okay, so C had 1 by 3, so it will distribute its 1 by 3 to B. Now in the next step we have A के पास 1 by 6, B के पास 1 by 3 and C के पास 1 by 6 plus 1 by 3 is 1 by 2. Okay. Sorry. Can anyone tell what will be the values for third iteration?
1 by 4, 1 by 2, 5 by 12.
Okay, let's try to calculate. So, okay. So now A has the value 1 by 6. So A will distribute its value to C, that is 1 by 6. Okay, so A had the value 1 by 6. It is sending all its value to C. Okay, now we'll see what is B. B is 1 by 3. So again, B will distribute its value into 1 by 6 and 1 by 6 and it will send to A and C. Okay, sure. And now we have C. C is distributing 1 by 2 to B. So this will become 1 by 2. So the values should be, A should be 1 by 6, B should be 1 by 2, and C should be 2 by 6, that is 1 by 3. This should be the values in third iteration. Any doubt, anyone? Is the calculation clear till now?
Yes, yes, ma'am. This one is clear.
Okay. So anyone else who want me to repeat, or if it is not clear? Okay, so I'll move on. ठीक है, तो अब network में क्या होगा? This will keep on repeating. Okay, so this distribution will keep on repeating, and there will be a point where the values will converge. Okay, the values will converge and there will be no further increment or decrement in the values. Okay, so I want to show you this with the help of the Excel sheets. Okay, let me open the Excel sheet. Okay, suppose I have A, B, and C. Initially, we had the values 1 by 3. B had the value 1 by 3. Sorry. Why is this happening? Let me check it. Okay. Okay, so A had value 1 by 3. B had value 1 by 3. And C had value 1 by 3. Okay, so now what was the value of A? Sorry, what was the value of A? A was B divided by 2, right? The value that B was getting. Okay, so the value that B was, that A was getting was always the value that B had divided by 2, right? Is it clear? The value, the initial value that B had, we had divided it into 2. So A was always getting B divided by 2. So we will say B divided by 2. Now, what is B getting? B was getting C value, right? So B was getting all the resource from C. So this was equal to C. Okay. And then C was B divided by 2 and A, right? So the cost of C was A plus B divided by 2. Okay. So see, these were the values that we got at second step. Okay, so now why I'm showing in Excel, because it's really easy to see the convergence here. Okay, so because Excel has this capability, suppose I copy this and I paste it here. So what I will get the next iteration like this.
Ma'am,
Okay.
ma'am, sorry to interrupt. C value was half of B and whole of A. We have,
Yes.
oh, my bad. That's right. Thank you.
Yeah. So that is the formula here you can see, right?
Yeah, yeah.
Okay. So now if I select this, and I drag it, so I'll keep on getting the values. Okay, so you can see that there is minor difference only that is happening here, but let us try to see that, like I initially claimed that in the matrix, if you keep on distributing the values like this, there will come a point when there will be no increment or no decrement. But here you can see that minor increment and minor decrement is happening. But then again, let's try to do it for more iterations, even more iterations. Okay, so yeah, so bingo, this is the point where convergence happens. Okay, so in this example, you can clearly see that if you keep on distributing the values in your network, in your directed network, so there will come a point when the values will get converged. Okay, so there will be no increment and no decrement after that. Okay, so here you can see that the value is 0.2, 0.4, 0.4. The summation of these values is 1. Okay, so that was the value that we started with. Initially, we started with value 1, and we have seen that the values, they like with the increment, when we iteratively distributed the values or the resources in the network, there came a point when these values converged. And when they converged, there was a specific score with each and every node. Okay, and this particular score can tell the importance of the node. So here, node B and C are more important than node A. Okay, so with this method also, we can try to identify which node is more important and which node is less important. Okay, so we will be discussing this notion again in more detail. So let's take a break of 10 minutes, and I would like you to, open your notes and quickly revise eigenvalues and eigenvectors before we come back. Okay, so yeah, and also like we can discuss if you have any doubts like after we come from the break. So up till now, is it clear? Any doubts? And I hope the explanation was like good enough so that you can appreciate that how the values are converging in the matrices. So this is true for any network. Okay, so currently we have taken only 3 nodes and we have seen that how the values converge. So you take any network, the values will converge. So I'll give you a homework. So maybe for a homework, you should try to do the same experiment with a network of maybe 5 nodes. Okay, so check with the 5 nodes and check if the values converge or not. So you will see that values always converge. So yeah, with that, we'll take a break. And like till now, what we have done is we have tried to understand the notion behind eigencentrality, and we have tried to see that how the values they converge. Okay, so now after the break, we will be discussing the derivation of the eigencentrality. We will be discussing that how you derive the formula. What is the formula for calculating eigencentrality? So yeah, with that,
Ma'am, quick question.
yes,
I wasn't paying attention earlier. What is the title of this topic that we are studying today?
centrality. How do you
Central. Okay.
calculate importance of a node?
Thank
So
you. Thank
earlier
you.
we have calculated in the previous lecture, we have seen 3 methods. This is the fourth method. And on this method only, the PageRank algorithm is based on the Google's
Thank you.
algorithm. So yeah, so it's a very important algorithm. So that's why I am discussing it in little more detail. So yeah, okay. Okay, so welcome back to the class. So now, if you want, you can note down this derivation in your notebooks, because like this derivation is not there in the slides today. Okay. Okay, so now basically we will be studying about eigencentrality. Okay, so we will be seeing that how mathematically we can derive eigencentrality. So I hope my screen is visible to everyone. Everything is fine. So yeah. Okay, so now what is the basic idea behind eigencentrality? The basic idea is that the popularity of a node depends on the popularity of its neighbors ठीक है? The basic idea is that popularity of a node, it depends on the popularity of its neighbor, which further depends on the popularity of its neighbors and so on. Okay, so the popularity of a node depends on the popularity of its neighbors. Okay, and the popularity of neighbors further depends on their neighbors and so on. Okay, so this is the definition of eigencentrality. So if you see, the definition is recursive. So this is a recursive definition where we have to calculate the importance of a node which depends on its neighbors. The importance of the neighbors further depends on their neighbors and so on. Okay. So now before actually seeing the derivation of the formula, first of all, there are a few prerequisites that you should know. Okay, so I will discuss this few prerequisites. The first prerequisite is that when matrix is multiplied to a vector and it is iteratively multiplied, okay, so we have earlier also seen that the values converges. Okay, so now whatever we have seen in the example, in the last example, the same network can also be represented in the form of a matrix. Okay, and if we keep on dividing that matrix to a vector iteratively, then at a point it will converge. Okay, so for example, like this was the network we discussed. Okay, so you can see this network can be represented in this form, in the form of a matrix, and the matrix can be multiplied to another vector. So when we keep on multiplying, so basically what we have studied before, I am telling you in the matrix form. So when you keep on multiplying a matrix with a vector, then at a point the values will converge. Okay, so yeah, this is the first prerequisite that you should know about matrix multiplication with vector. Okay, so now there is second prerequisite that you need to understand in order to, understand this particular derivation. So now suppose you have these two vectors. Okay, so whenever you have two vectors and you need to perform an addition, so how you will perform the addition if you remember from vector algebra? So this is your vector number one, this is your vector number two. This will be the solution of vector A plus vector B. So vector C is the answer for a vector A plus vector C. So now if you closely observe these two, okay, so whenever we perform addition, if there is one vector that is like quite larger than the other vector, okay, so then the resultant will be very close to the direction as well as to the magnitude of bigger vector. Okay, so we can see that even the magnitude or the direction is very, very similar to the bigger vector. Okay, so now if you understand these two prerequisites, I will also give you some basics about eigenvalues and eigenvectors. So third prerequisite is that you should know some basics about linear algebra, about eigenvalues and eigenvectors. Okay, so you know that the eigenvector formula is AV is equal to lambda V, where this is the eigenvector and this is the eigenvalue. Okay, so now if I have a matrix of size 2 cross 2, okay, so if A is of size 2 cross 2, then anybody can tell me how many eigenvectors can we have? So have you studied linear algebra before?
Yes, ma'am.
Okay,
First
how many?
semester, that's what we did.
Okay, okay. Is there anyone who has not covered this topic, linear algebra? Okay, so can you tell me, like, if we have a matrix 2 cross 2, how many eigenvectors it will have?
Two?
Correct. So if we have a 2 cross 2 matrix, then this particular matrix will have two eigenvectors, and these vectors will be independent of each other. Okay. Now the third point is that any vector, hmm, any vector can be represented by the linear combination of these independent eigenvectors. Okay, so any vector that is two-dimensional, any point on two-dimensional can be represented by the linear combination of this eigenvectors. So suppose Z is any vector that can be represented by linear combination of V1 and V2. Okay, so these are the 4 points that you should know before we move further. Okay, so suppose we have AV. Okay, so AV can be represented as if A is my matrix, V is any vector, then this can be represented by A lambda V1 plus beta V2. Okay. So this is the linear combination of the two eigenvectors. These are the two eigenvectors, and this is the linear combination of these two vectors. Hmm. Okay, so now we will move back to our derivation. So these were the prerequisites. Maybe I'll share these notes with you. I think that will be better, right? So yeah. So now we have studied that eigencentrality depends on its neighbors, which further depends on its neighbors, and so on. So now the centrality, whenever we are calculating the centrality is calculated by summation of all its neighbors. Okay, so now let us suppose, let the initial popularity of node I is xi0. Okay, so let us assume that the initial popularity of a node xi is xi0. Now, after we have seen that at each steps the costs get distributed. Okay, so now after first step or first iteration, what will happen? The resultant popularity will be sum of neighbors popularity. Okay, so the popularity of the node will be sum of the neighbors popularity. So this calculation we have already done before. So now if I want to represent it in the form of matrices, so how can I represent it? The popularity of node xi at first iteration is equal to, this is my adjacency matrix. Okay, so I will see aij's for all j values into xj 0. Okay, so what does this formula represent? See, these aij's, it will give me all the neighbors of node xi. So now suppose this was my node I, okay, and its initial cost was xi0. Okay, and these are all the neighbors. Okay, these are represented by aij. Aij is the adjacency matrix, and in adjacency matrix, Aij has a value if like this is a neighbor to I. Okay, so this is all the nodes 1, 2, 3 up till j. Okay, so all the nodes that will be neighbors to this particular node. And suppose these nodes, they have initial cost as aj0. Okay, so aj0 is the expression that is telling the cost that was there before calculating, like initial cost that these particular neighbors had. Okay, so xj0 represents the initial cost that the neighbors were having. Okay, the cost that neighbors were having at step 0. So that you have joined with the adjacency matrix, and this particular expression, it gives you the cost of node xi, or the popularity of node xi at step 1. Up till now, is it clear? So the cost here, the cost of xi at 1 is equal to aij xj 0. Up till now, any doubt, anyone? This expression is clear to everyone? Yes or no?
Yes. Yes,
Yes,
ma'am.
Okay.
ma'am.
Okay. So now you know that we apply these steps recursively, and there will come a point when the values will converge. Okay, so that we have seen in the Excel sheet, that if we keep on applying, if we keep on iteratively repeat this step, there will come a point when the values will converge. Okay, so now let us keep on applying this value, and let us suppose these values, they converge after time t. Okay, so if they converge after time t, what will be the cost of node xi at like time t? So let us assume that values converge at time t. Okay, so now what will be the cost of the nodes at t? It will be equal to adjacency matrix into the cost of the nodes that were there at the previous step. So is this formula clear? Whenever the values converged, okay, when the values converged, at that time, like if we want to calculate the popularity of the nodes at that time, okay, what we have to do is we have to consider the popularity of all its neighbors that were there at one timestamp before the convergence happened. So is this clear? Is the scenario clear? Any doubt? Okay. So now we will keep on repeating this process. Okay, so what will be the popularity at xt minus 1? The popularity at xt minus 1 will be a into xt minus 2. Okay, so this is equal to a square x t minus 2. The popularity at xt minus 2 will be equal to a3 x t minus 3 and so on. Okay, we will reach to the point at x 0. Okay, so we will reach to the point where there will be no further improvement. Like this will be the x0 was the initial cost, right? So now we have derived a formula for xt. So what is xt? Xt is equal to at x0. Okay, so this particular formula is called as power method by hotlink. Okay, and let me assume. So let me assume this was equation 1 and this is equation 2. Okay, so now you can see that xt can be represented by at, okay, and like the initial cost of the nodes that we have. Now see, this is a vector, right? So this is a vector and we have assumed that initially, like any vector can be represented by the linear combination of its eigenvectors. Okay, so we can represent this particular vector by the by the linear combination of eigenvectors of this matrix. Okay, so now let x0 be the linear combination of eigenvectors of matrix A. So I would like suggest that you should brush up your linear algebra for this course as well. Okay, so now x0 can be represented as suppose the x0 represent the initial popularity of all the nodes and there were n nodes in the network. Okay, so we can represent this particular vectors as okay, and this can be represented by the linear combination of all the eigenvectors. So the linear combination will be c1 v1 to vn plus c2 v1 v2. Okay, so this is the linear combination of eigenvectors. So now you can represent x0 like ci vi. Okay, so this is equation number 3. So we have derived an expression for x0 here. Okay, so this expression we will input in equation number 2. So now xt. xt is the popularity that we want to calculate when the values get converged. Okay, so xt will be equal to 80, and uh, we will put equation 3 in equation 2, summation of ci and vi. Now this is equal to summation of ci and vi. You know, vi can be sorry, we can represent it by ai, at, vi. Okay, by using the eigenvectors and eigenvalues, this expression can be represented by ci lambda it vi. Okay, so yeah, so now like we have calculated the cost in the expression of eigenvalues and eigenvector of the matrix that we had. Okay, so the cost that we are going to get after applying in this network using the eigenvector centrality, it depends on the eigenvalue and eigenvector of the matrix that we are considering. Okay, so now I would also like to take one more example here. Suppose like you know that the eigenvalues will be different. So for a particular matrix, the eigenvalues will be different, and like lambda 1 is always greater than lambda 2. Okay, so now suppose we have lambda 1 as 3 and lambda 2 as 2. Let us assume this. Okay, so now when we square it, so square of 3 is 9, 2 is 4. This is 27, this is 8. Okay, so you see that 3 raised to power may be 100 and 2 raised to power 100. There will be a huge difference in these two values. Why there will be a huge difference? Because you can see that when we square these values and we keep on squaring these values, we keep on multiplying these values, there becomes a huge difference in these two values. And suppose we divide 2 raised to power 100 by 3 raised to power 100, this will be approximately equal to 0. Okay, now coming back to this particular expression, let me further elaborate this particular expression. Okay, so this can be written as C1 lambda 1 party. Is my screen visible?
No, ma'am. Cannot see your PPT.
Okay, just a second. Okay, so this expression can be expanded as this particular equation can be expanded as Ci lambda 1 raised to power Ti Vi. Okay, plus summation of, let me take the first eigenvalue outside. Okay, so this will be Ci lambda I 2 lambda 1 raised to power T Vi. Okay, so this value will be approximately equal to 0. So from this example, we can say that xt is dependent upon Ci, Vt and V1. Okay, so the popularity correspond to principal eigenvector. So principal eigenvector is the first vector. Okay, so the popularity or the final popularity which converges is approximately equal to or is equal to the principal eigenvector. Okay, so yeah, so from this, it is clear that if you want to calculate the importance of a node based on the importance of its neighbor. So how you will calculate it? You will calculate based on the principal eigenvector. Okay, the values in the principal eigenvector. So you will get this is the matrix, and you will calculate the principal eigenvector for this matrix, this particular matrix, and the principal eigenvector, that is maybe the values v1, v2 up till vn. These will give you the importance of each node. Okay, so some of the concepts might not be very clear in today's lecture, but I would suggest that you should again see this particular derivation. You should brush up your skills on linear algebra, especially eigenvalues, eigenvectors, the formulas involved. And if you are clear with those formulas, then you can easily understand this particular derivation. So the derivation is that importance of a node depends on the principal eigenvector. Okay, so now there is one problem. Indirected networks. Okay, so anyone can identify that what can be the problem with this particular centrality calculation in the directed networks? Anyone can identify?
Ma'am, in
Anyone?
directed network, if a node is a sink node, then eigenvalue will be 0,
Right.
and that will create a problem.
Right. So, yeah, so if there is a node and there is no outgoing edge from that node, okay, so in that particular case, this can create a problem. Okay, so now in order to overcome that particular problem, what is the formula that was for eigencentrality for the directed graph is that they initially distributed some minor centralities to each and every node. Okay, so they initially distributed these centralities to each and every node. So now the formula become, first of all, I'll write the problem. See, the in degree of a node can be 0. So if the in degree of a node is 0, okay, so then like none of the neighbor will be contributing to its importance. Sorry. Okay, so if the in degree of a node is 0, then none of the neighbors will be contributing to its importance. So according to the definition of eigencentrality, we know that the centrality, it depends on the popularity of its neighbor. So in this case, we will not be able to calculate the centrality of this particular node. Okay, so if the like in degree is 0, then 0 popularity cannot be propagated in the network. Okay, so this can be tackled by sprinkling minor popularities to each node. So now what will be the formula for the eigencentrality in the directed graph? It will be Aij xj plus beta. So we have added these two constants where beta is the small initial value for each node, and alpha is the readjustment constant. Okay, so now up till now we have studied about the notion of the importance, eigen centrality, and like how the hubs and authorities they affect this centrality. Then we have seen that okay, these centrality values in the network they converges. Okay, we have seen an example, and then we have derived the formula for calculating the eigencentrality that basically depends on eigenvectors. So now we have identified one problem, and we have seen that how the eigencentrality can be calculated for directed graphs, and this is the formula to do that. Okay. So now next, there is this very important algorithm called as PageRank algorithm that is used by Google. So this PageRank algorithm, it depends on eigenvectors. Okay, so basically by using the eigenvectors, it calculates the eigenvectors for all the web pages, and based on that, they rank the web pages or sort the web pages and give us the results. Okay, so whatever pages you see, the algorithm behind it is calculation of eigenvector centrality, eigenvectors. Okay. So now we will see what is the formula for PageRank algorithm. The formula for PageRank algorithm is very similar to what we have seen in the last formula. That is the formula for eigencentrality. So in this, we have xi is equal to alpha rho j aij xj divided by k j out plus beta. Okay, so basically whatever the popularity is there, okay, so whatever the popularity is there, that is divided by the number of outgoing edges. So this is what we have demonstrated in the initial example that I gave you. So from the node B, there were two nodes, there were two outgoing connections. So because there were two outgoing connections, so the cost of B, that was divided into two. Okay, so if there were three different nodes to which B was connected, so then the cost will get divided into three. So what the page rank algorithm does is it divides the initial cost, the cost that was present in the previous step. So it divides that cost with the outgoing edges. Okay, so yeah, so this is the only change in the page rank algorithm. So yeah, so this was all about today's lecture. So yeah, is there any doubt, anyone?
Ma'am, in that page rank equation, what was the denominator there?
This is the outgoing edges, number of
Okay,
outgoing edges.
okay,
Yes.
number of, okay.
So we have seen that example here. So in this example, we have seen that there were two outgoing edges. So the cost got divided into two. So whatever like we ran in this particular demonstration, so similar way the PageRank algorithm works. So the PageRank algorithm works in a very similar way that I have shown you the demonstration here. So yeah, we will stop here, and yeah, so I would like you to, do this derivation again, understand the concepts clearly, because there will be questions on, like there will be logical questions on eigencentrality in the paper. So yeah, so that's why you should understand this concept very clearly, understand your linear algebra basics very clearly. So in the next lecture, we will be covering the community detection algorithm. So today we have finished the topic of centrality calculation. So we have seen a total five algorithms. So first one was the degree centrality, that was very easy to calculate, very easy, very intuitive. That only depends on the number of neighbors that a particular node has. Okay, so what is the difference between degree centrality and the eigencentrality? In eigencentrality, the centrality not only depends on the neighbors, it also depends on how important these particular neighbors are. Okay, so that importance is calculated by the eigenvectors. Okay, so we have seen degree, we have seen eigencentrality, we have seen closeness centrality. So closeness centrality, it basically calculates the nodes that lies in the center of the network. ओके सो जो भी नोड सेंटर में लाई करेंगे, इफ यू वांट टू स्प्रेड सम इंफॉर्मेशन, यू शुड गिव दैट इंफॉर्मेशन टू दोज नोड्स, so the information will spread really quickly. Okay, so that was closeness centrality. After closeness centrality, we have covered betweenness centrality. So when betweenness centrality come into picture, so whenever you have these two groups, okay, and there is one person in between who is dependent for passing the information from one group to another. Okay, so whenever you want to identify these type of nodes that are important in connecting two groups or two clusters, okay, so those are the situations where you calculate betweenness centrality. So then after that, we have also seen the PageRank algorithm. So PageRank algorithm is a very important algorithm that depends on eigenvector calculation. So with this, we have finished the topic of how to identify important nodes in the network. Okay, so now applying any one of these algorithm based on our application or based on the complexity. So also you should, whenever you are applying these algorithms, you should, take into account that what is the calculation time, what is the time complexity for each of the algorithm. So the betweenness centrality and the closeness centrality, they involve calculating the shortest paths. So whenever we need to calculate the shortest path, again, the computation becomes heavy. Okay, so whenever you have very large networks, in those cases, computing betweenness centrality and computing closeness centrality will become very time consuming methods. Okay, so based on the size of the network or based on the application, you should decide that which amongst these 4 5 algorithms that we have discussed should be used to find out the importance of the node. Okay, so now after understanding that how we calculate the importance of the node, the next aspect that we are going to study is how you identify the communities in the network. Okay, so how you identify the clusters in the network, how you identify that which nodes are more connected than the other nodes. So these are some set of algorithms that we will be covering in our next lecture. Okay, so before going to the community detection, I would like you to think about a very interesting question in social media analytics. So the question is that, okay, we have seen that Google applies PageRank algorithm and that is based on matrix. Okay, and okay, for the matrix, we calculate principal eigenvector, and so principal eigenvector gives the sorted pages or the ordering in the pages. So, but the question is, how do you calculate the matrix? अब हमारे पास इतने सारे web pages हैं. Okay, there are so many web pages, there are so many interlinks. So how would have the people who actually, came up with this company, who actually first discovered this algorithm, so how did they form this matrix that represent the network? So that is the question that I give you for a homework. So in the next lecture, we will start our lecture by discussing on this, that how this network was formed, how they stored this network, and how like they got the data about this. So yeah, so these are the two topics that we will be covering. Also, like next Saturday, I am traveling. So mostly I will schedule the next lecture on either on Monday or Tuesday. So mostly I will be rescheduling the next lecture to Tuesday. So next Saturday, you people won't be having the class, but you will be having a class on Tuesday, 7 to 9. So that is the time when I will be scheduling the class. All right. So with that, we will end the lecture. Anybody want to ask anything?
Ma'am, is there any topics that we have to concentrate more for the midsem exams, ma'am? You have that
Okay,
message.
so Basically, like I'll be mostly focus on giving the numericals. So whatever topics we have covered, that can be centrality, that can be like the shortest path calculation, Dijkstra algorithm. So you should basically focus on the how you'll solve the questions based on that, those particular formulas. You should understand those formulas clearly, and you should be able to answer the problems based on those formulas. So yeah,
Okay. Okay,
yeah,
sure. Thank you.
yes. So whatever the topics are covered, you basically I will be testing the understanding of the lectures. So are you understanding whatever I am delivering in the class? So yeah, that will be the focus, and based on that, you can prepare for your midterms.
Ma'am,
All
when you
right.
said Tuesday, did you mean 9th or 16th?
When I say Tuesday, Tuesday is 16th, next Tuesday.
Thank you.
Yeah, so uh, yes, so 16th, I'll take the lecture.
So, ma'am, is that topic also included in midsem?
When is your midsem scheduled?
21st, 20th and
21st.
21st.
Okay, okay. So I'll check if the topic is difficult to understand. So if the topic involves lot of logistics, so then I'll not include that lecture. But if it is like straightforward formulas, so then I'll give, like, depending on the difficulty of the lecture, I'll decide. So if it is difficult to understand, like the one that we have discussed today, so if it is like this lecture, then I will not include it in the midsem. But if it is like our fourth lecture, or the fifth lecture, like there were some formulas, and they were like pretty straightforward to follow. Okay, so if it is like that, then I'll put that in exam.
Sure, ma'am.
Okay. So yeah, with that, we'll end the lecture. Thank you, everyone. Thanks for being a lovely audience. See you
Thank you, ma'am.
next Tuesday. Yeah. Bye.
Thank you, ma'am.
Thank you.
And all the best for your midsem preparation.
Yeah, thank you.